Hello, my name is Isabel Hernandez. I am a current undergraduate student here at the University of Michigan, and today I'm going to be talking about Root Fame, a series of analysis scripts for the investigation of fission events. To start off with, one of the many signature characteristics of a fission event is the emission of neutron and gamma rays in coincidence. Given millions of these instances of fission events, there was a need to form coincidence of observables as well as to discriminate and determine the correlation of these emitted particles. Our processing script, Root Fame, is designed to process, compass, and MIDAS experimental fission data and provide the user with PSD, kinematic, and time-of-flight figures. Root Fame is also designed to be user-compatible, providing system and characterization, error analysis, and data cuts of a user's unique experimental setup. Our processing script, Root Fame, has proven to accurately depict a wide range of experimental systems, including Chi-Nu at Los Alamos National Laboratory and FS3, the fission sphere here at the University of Michigan. It has worked with plutonium-242, plutonium-239, and californium-252 data. Today, however, I'm actually going to be talking about our artificial neural network that was designed to work in tandem with these root processing scripts. Specifically, we are designing this neural network to infer information from the Root Fame output structure to ultimately determine the impact of crosstalk and room return events on an experimental system. The NNSA's mission is to prevent nuclear weapon and proliferation and therefore reduce the threat of nuclear and radiological terrorism around the world. Analyzing the relationship between these fission observables will further our understanding of fission in SNM and therefore contribute to NNSA's non-proliferation objectives. All right, to provide a script, to provide basically analysis of crosstalk events, we wanted to make a script that would continuously analyze the relationship between known experimental variables and therefore isolate crosstalk events. We did this by simulating our system, the FS3 sphere, in MCMPX Polimi on 1E7 MPS. From there, we took the collision file, ran it through another processing script that basically looked at each particle, each event, and determined if it was a crosstalk event or a regular event, just given the history, the scattering, and the generation. We then developed artificial neural network using the Root programming language, specifically the T-multilayer perceptron class in Root. We then normalized our input, our two input nodes being neutron integral or light output and neutron time or detector time. And then we restricted the output that the neural network would give us, which is the flag 0, 1, 0 for crosstalk, 1 for regular event. We restricted it between 0 and 1 because we just wanted the neural network to give us a continuous variable between those two. We then trained it on an epoch of 100, which means that our artificial neural network read the data 100 times and learned it. And then we used the BFGS learning method. All right. The top left figure shows the dependence of the neural network on each input variable. Basically breaking this down, our neural network seems to be more influenced by neutron time of flight than neutron energy, which is pretty interesting. We'll get into that. We'll further understand the relationship. The top right figure shows the error of the artificial neural network, whether it says it's flag 0 or flag 1, and the actual flag 0 or flag 1. So as you can see, we have quite a few events with an error of close to 0. We also have a significant number of events with an error close to 1. And this shows that basically our artificial neural network is discriminating accurately against 33% of crosstalk events in simulation, which is really actually very interesting. It's better than 0, which we had before. But we wanted to see how this accuracy matched up to what we usually do, which is a graphical cut. So as you can see here, the figure on the bottom left is just neutron time versus neutron light output. And the figure on the bottom right is the ratio between just neutron time versus light output of flag 0 events and then just all events. So as you can see, the yellow region represents the concentration where there's the most concentrated of flag or crosstalk events. And so we took a graphical cut of this region. And this actually showed that taking a graphical cut had an accuracy of identifying crosstalk events for about 11%. So our neural network is actually 3 times more accurate than taking a graphical cut to discriminate against crosstalk events, which is very interesting and very promising. We would like to thank Los Alamos National Laboratory with working with the KaiNU system, as well as Oak Ridge National Laboratory. I will be actually interning this summer at Lawrence Livermore National Laboratory, so that's another, with the help of MTV. So, and then as well as I'd like to thank the MTV MCMPX Polemi workshop because a lot of what we learned there contributed to this, this project. In conclusion, our neural network scripts provide a repeatable and relatively accurate method to isolate crosstalk and rumor term events in unique configurations. Future work includes optimizing the model to minimize identification error, adding maybe another input node for PSD, and considering the severity of independent crosstalk events, as well as maybe applying this to experimental results. So thank you for your time, and I hope I will see you at my breakout session.